Hi, welcome to Math for Adults Foundation. Today we will be thinking in patterns related to how many diagonals are in polygons. We're going to be using geogebra.org. So go there now and I'll show you how to use it. First, we are going to draw a polygon with 3 sides. You probably already know the name of it. It is a triangle. Next, we'll draw a polygon with 4 sides. It is called a quadrilateral. You always have to go back to the first vertex and click on it to close it, because polygons are closed figures with straight sides, and they're 2-dimensional. Now we're going to click on our segment tool, and we're going to put in some diagonals. So there's a diagonal going across our figure, and here's a diagonal. So there are 2 diagonals in a quadrilateral. Now we could try to put a diagonal in a triangle, but then we just get a side of the figure, and sides of the figures are not considered to be diagonals. Next, let's go on to the 5-sided figure. Try it on your own, and the 6-sided figure, and put in the diagonals, and then we'll make a table with our data. Okay, when we had a 3-sided polygon, a triangle, we had 0 diagonals. When we had the 4-sided polygon, the quadrilateral, we had 2 diagonals. And I hope you found that when you drew the pentagon, that there were 5 diagonals. Now, to get how many diagonals are in the 6-sided figure or the hexagon, it can get kind of confusing. So let's try to figure out a way to keep track. Let's look at how many diagonals there are per vertex. So we can draw 1, 2, 3 for the first vertex, and we could draw 3 for the second vertex. But when we get to the third vertex, there's some overlap. There's already 1 drawn. So yes, there will be 3 diagonals at the vertex, but there's some overlap, and here as well. So to figure out the number of diagonals, we might be able to be tempted to say 6 vertices times 3 diagonals for each vertex, but that wouldn't take into account any of the overlaps. We actually have to cut that in half for the overlapping vertices. So there would actually be 9 vertices in the hexagon. And we can keep track of that now by looking at the number of diagonals per vertex. So for the hexagon, there were 3 diagonals per vertex. Back here at the pentagon, there were 2 diagonals for each vertex. 5 times 2 is 10, but then cut that in half and you get your 5. That's right here. For the quadrilateral, there was only 1 diagonal per vertex. And for the triangle, there were 0 diagonals per vertex. So you can see the pattern. The number of diagonals per vertex is always 3 less than the number of sides. So we can say the number of sides, S, and then the number of diagonals per vertex is S minus 3. And to get the total number of diagonals, you can do what we did with the hexagon. Take the number of sides times the number of sides per diagonal, and then to account for any overlaps, we have to cut that in half. So it's S times S minus 3, all divided by 2. Okay, you might also notice that the diagonals per vertex is going up by 1 per stage, and the number of diagonals is going up in an interesting way. First, it goes up by 2, and then at the next stage, it goes up by 3, and the next stage, it goes up by 4, and so on. So now if you wanted to check it out for 10